Hello everyone and welcome to this deep dive into object lifetime in C++, where we will explore a powerful but often overlooked optimization called empty base optimization, or EBO. We will also talk about why it matters in terms of memory efficiency, object layout, and performance-critical C++ systems. Let's get into it. In C++, every object must occupy a unique memory address. Even if a class has no data members, it must still consume at least 1 byte of memory. This ensures that different objects of the same type don't alias the same address. Here is an example. Even though empty has no data, E1 and E2 each get a unique address. Why? Because the standard requires that two distinct objects occupy different locations. Let's verify the size of an empty struct. 1 byte. That's the cost of being empty. But now imagine this. What if you are building a class that inherits from an empty base? Would it still take up that extra byte? This is where empty base optimization kicks in. Let's see how. If EBO is enabled, and in almost all modern compilers it is, then derived will only be the size of an int, not an int plus 1 byte. The compiler is allowed to treat the empty base as taking up no space. This is key to optimizing object layout. Why does this matter? Imagine you are designing a class with policy-based design or traits. For example, take this code. If policy is empty, empty base optimization makes it free in terms of memory. You can now use tag dispatching or behavior injection at zero runtime cost. Let's make it more interesting with two policies. If both P1 and P2 are empty, empty base optimization lets the combined object still be the size of just an int. But there is a catch. Empty base optimization only works when the empty base is not repeated. If the same empty class appears multiple times in the inheritance chain, the compiler must assign each a unique address unless it's explicitly optimized away. Here is a problematic case. Here empty appears twice, once in A and once in B. This leads to ambiguity and disqualifies EBO in many cases. You get what's called the diamond problem. To resolve this, you would need virtual inheritance or redesign. Now let's talk about a real-world use case, the stud function implementation. It uses type erasure internally and often stores functors or function objects. Sometimes these functors are stateless. With EBO, storing a stateless functor doesn't take up extra space. That means calling a lambda that captures nothing is as cheap as a regular function pointer. Internally, the lambda is empty. Thanks to EBO, function uses minimal memory for storage. Another key use of EBO is in stud tuple. Let's look. Despite having two elements, the size of t is still the size of an int, assuming EBO is applied. That's an optimization that you get for free, just by designing your types with EBO in mind. So, how do you leverage EBO in your own types? The simplest way is to inherit from empty types, instead of embedding them. Here is an example. This way, if t is empty, EBO can kick in and eliminate its storage overhead. Compare that to this. Here, even if t is empty, the compiler must still allocate space for it, because it's not in the base subobject. There is another variation of this idea, used by the standard library and others, compressed pair. A compressed pair is a pair that uses EBO for one or both of its elements, depending on whether they are empty. Let's say you write something like this. If T1 or T2 is empty, the pair still consumes minimal space. This is a great trick for STL-like containers or adapters that carry allocators or predicates which might be stateless. Of course, you need to be careful with multiple inheritance and ambiguity, especially if both T1 and T2 are of the same empty type. A common way to solve this is to introduce tagging. This makes each base unique and EBO safe, even if T is the same type. But what about visibility? EBO often works best with private inheritance, because it avoids exposing the base class's interface, which might not be desirable in a compressed object. Now, let's briefly consider object lifetime. Since empty bases can be optimized away, does that mean their constructors or destructors are also omitted? No, it does not. The compiler still calls constructors and destructors of empty base classes, unless they are trivial. EBO only affects memory layout, not the semantic behavior of your code. So if you rely on side effects in your base constructors, you are still safe. Even if logger is empty in terms of data, the constructor runs and prints the message. So remember, EBO is layout optimization. Lifetime semantics remain unchanged. Let's recap quickly. In C++, even empty classes take up space due to object address rules. EBO allows the compiler to eliminate the space overhead of empty base classes. It's a powerful technique used in the STL, std tuple, std function, allocators, and more. To leverage EBO, inherit from empty classes instead of embedding them. Watch out for multiple inheritance of the same empty class. Tagging can help. EBO doesn't affect constructor or destructor calls. Object lifetime remains fully honored. EBO is a subtle but crucial part of writing memory-efficient C++. Once you understand it, you start to see how libraries like the STL pull off their zero-cost abstractions. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one.